Hello, we're going to talk today about computers, section 1.2 in the book, mostly about hardware and some of the concepts of computers that relate to programming, although there's no expectation you will understand the machines, but rather just a few introductory ideas. Okay, hardware consists of really four major categories. I have five here, the middle one being a combination of the first two. The first is an input device. To get information into the machine, we have to input it. That means to bring it from an external device, such as a hard drive or a keyboard, and bring it into the memory of the computer, where the programs will run and deal with the data. Output devices is just the other direction. The data flows from memory outward to external devices, perhaps displayed on a monitor or printer or stored on a hard drive. Most input and output devices only go one direction. Keyboard only inputs, monitor only outputs. But some devices are a combination of input and output. And often that's hard drive, uh, various types of storage media, DVDs, thumb drives, etc., or communication sockets. Every time you open a web browser and hit a website, you're using communications and you're sending data to and receiving data from those remote websites. There's the CPU. It is the brains of the operation. It controls the operation and the flow of a program, and it does computation and various logical operations. But memory, I think, is the real key here. It holds the instructions and the data. So it's the mind and the memory of what a program is and what the machine will do at any given moment. Now, the operations that a CPU does is hardwired or hard coded into the circuitry. So that doesn't change. But a program, by altering the information in memory, can make the machine work differently. Input. From the reference point of memory, we consider uh, that term input. Again, from reference point of memory, data from external devices or out there have to come in or be input into memory. That's how to keep straight what input means versus output. The external sources, again, often a keyboard, hard drive, communication socket, etc. Program instructions have to be input before the program can run. When you program, you'll write some source code, and it will be compiled into executable code that the machine understands. And that code will have to be input into memory before it's run. And when it's run, the CPU will interact with memory uh, to, to execute the instructions you give it. And if there's any data that your program needs that's not coded directly in the program itself, that has to be input. Things like asking for your name or test scores if we're averaging those, or other type of information that you would need has to be input into memory while the program's running so it can handle it. Output, again, from the reference point of memory, means to take information in memory and output it or put it out to external devices, often a monitor or a hard drive. Uh, Printers, communication sockets, etc., are other forms of output. But again, it's always the idea of moving information from inside the machine outward to external devices. The combination is some devices do both. CPU controls program execution flow. That is one instruction after another. Sometimes we need to jump around in a program because we don't always want to do the next instruction. We may want to do it, or we may want to skip it, or we may want to repeat some instructions multiple times. Those are called selection and repetition control structures, where we optionally execute an instruction or repeat an instruction. And the CPU controls that. The program is what defines what those instructions are and what that flow is, but the CPU actually implements that. The CPU manipulates data in some way. We may add some numbers, we may multiply numbers, we may test a number to see if it's larger than a value or see if two numbers are equal, on and on. The CPU does all that work. And the CPU also detects errors of certain types. It will figure out when something has gone wrong, and it will often signal the program that something broke. And many programs just terminate. That is, they stop running. And you get an error message sometimes. And I'm sure all of us have experienced that multiple times. The program just crashes. Okay, the memory is really the heart and the mind of the machine. It's what the machine knows or your program knows. It's what it remembers. It's the data it's computed or manipulated in some way. Think of memory as the boundary between external devices and the CPU. The CPU is kind of hidden away. It only operates on what's in memory. It can't see the outside world, but the outside world will move information into memory, that's input, and take information in memory and move it out to the external world, that's output. So the external world talks to memory, and the CPU talks to memory, but the CPU does not talk to the external world. Memory stores and remembers program instructions and program data. That's why it's so critical to have memory and to understand a bit about it, because everything the machine knows is stored in that memory. If you power off a machine, it forgets it all. And that's why when you boot up a machine on power up, it takes a while because it has to load things into memory. And then you have to tell it which programs to run. They have to load into memory before the CPU can touch them. All the information that's been input, information that's been processed, and is awaiting for output will be in memory. So memory is the single most important machine aspect for understanding programming. You don't have to understand much about it, but really the CPU, you don't need to know anything about it if you don't wish to. The fact there's input and there's output, that's generally about as much as you need to know. But memory, it's important to know a little bit more about it. For example, all memory in a machine that has power on has some value. A byte is the smallest unit of addressable memory. All bytes have a unique integer number that represents them. Starts at 0 and goes up to 4, 8, 16 gigabyte, whatever the machine has. Each byte has a unique address. No two bytes have the same address. And think of the address as house numbers. Assume we had a big long street called Memory Lane. Each house would have a unique number. If somebody were driving down Memory Lane and wanted to go to a certain house, all they'd have to know is its number, its address, and they would go to that house. Well, that's the way bytes work in memory. Each one has its own address. The machine refers to data by those addresses. We humans don't do that so well. We usually will call them by some symbolic designation like count or age or some other name that means something to us. The compiler translates between our symbolic notations and machine addresses or numbers. We don't have to keep track of those details. But all that memory has a value in it. There's some combination of 1 and 0 bits set on. Generally, we programmers have no idea what those bit patterns are. We don't know what numbers they represent. So as we learn to program, we'll learn the term initialization. It means to set memory to a known value before we use it. Imagine trying to do a math problem where you don't know the value of certain variables in the problem, and the question you're trying to solve is, what's the answer when you do these mathematical manipulations? Well, if you don't know the values, you're never going to figure out the right answer, or if you do, it's going to be accidental. So it's the same idea. Now, a byte is 8 bits. That means there's 8 binary digits. A binary digit has the value 1 or 0, and that's all. Which means in decimal terms, in the terms we're used to, a byte can have values between 0 and 255 for a total of 256 different patterns. That's it. That's all a byte can have. So the byte, as I said, has a unique address. It is the fundamental addressable unit of memory. That is, each byte has its own address, and the machine can address each byte individually. Program instructions and program data are stored in memory. They consume a certain number of bytes. Most pieces of data in the machine consume 2 or more bytes because 1 byte is just too small to store anything valuable. So some instructions are 32 bits long. That means it would take 4 bytes. Some instructions are 64 bits long. That means it would take 8 bytes to store one instruction or one piece of data. As a programmer, you rarely need to know anything about that. But you do need to know that instructions are stored in memory and data is stored in memory. And in some cases, we need to know the idea of addresses where data is located in memory. We don't need to know the actual number of where that data is located, but we need to know the concept. That will be explained more later. Since both program instructions and program data must be stored in memory, it makes sense that the CPU can't do any work unless they're stored in memory. It would have nothing to direct it what to do, and it would have nothing to work with. So thus, both instructions and data must be in memory. And everything other than single bytes are encoded in multiple bytes. And this usually takes clever thought and follows standards. I give an example here, the IEEE 754. If anybody's curious, what that is a standard that says how to encode floating point numbers in integer bytes. It's just the standard. The standard is so widely accepted that the CPU directly deals with that encoding mechanism of taking for a double type value, which would have 64 bits allocated to it. It has, I believe, 11 bits set aside for the exponent, 52 or so for the mantissa. Those are the digits, and then a bit or two. I think just 1 bit for the sign, whether it's positive or negative. But those are encodings. A different standard could have been chosen, but this is the one that was chosen. So we encode floating point numbers, which represent real numbers in mathematics. They only approximate them, but they do represent them. We choose an encoding scheme because everything, again, is a small integer or a combination of bytes of small integers. So anything that's not truly that has to be encoded. And that's something as programmers you will learn more about. You won't have to master it, but you'll at least need to be aware of it. Now, finally, software. Software is not technically a part of the machine, but it is what directs the machine. It's the set of instructions. Your operating system, word processor, game, and various other programs are software. They tell the machine how to work, what to do. And as a programmer, you will learn how to write software to direct the machine to do various actions to solve problems. Programs make a machine behave differently. Different programs cause different behaviors. Not every program does exactly the same thing. Otherwise, we would only need one program, but we need thousands because they each do something different. The machine has predefined limits and actions that it can do. Certain instructions down in the very CPU, there's a certain limited set of instructions a machine can do. So software really is the art of choosing which instructions to do and in what order to make other larger problems solvable. And you don't really have to know in general what those instructions are because programming languages will hide a lot of that detail, but you will deal with higher level concepts. But still, it'll be instructions, and ultimately the machine has to execute them. So programming is the art and science of directing the computer in solving algorithmic computational problems by manipulating numbers stored in memory. It's not that complicated. Well, on the surface, the details, in fact, are very complicated, but learnable. That's what this course will help you do, is learn that.